Capacitors and resistors in AC circuits. First of all, looking at resistors in AC circuits, if we connect a voltmeter across an AC signal generator, we can determine what the voltage is going to be across the resistor connected in parallel with it. By keeping the supply potential from the signal generator constant, we can check using the voltmeter. We vary the frequency of the supply and measure the corresponding current in the circuit. If we do this, we can see that the current remains constant within the resistor circuit, irrespective of the value of frequency. The opposition to the alternating current is called impedance, and like resistance is measured in ohms. As the frequency of the supply is increased, the current in the circuit stays the same. And that's because the impedance of a resistor is not affected by changing the frequency of the current in the circuit. When we repeat the same procedure for a capacitor, we can see that as the frequency of the supply is increased, the current also increases. It's a directly proportional relationship. The impedance of a capacitor is affected by changing the frequency of the current in the circuit. The current in the circuit is directly proportional to the frequency of the AC supply. As the frequency of the current increases, the size of the current increases. The impedance of a capacitive circuit is inversely proportional to the frequency of the supply. That is, as we increase the frequency of the supply, the opposition to the current decreases. At low frequencies, the impedance of the capacitor is very, very high. That is, the current will be low. At high frequencies, the impedance of the capacitive circuit is very, very low. Therefore, the current is going to be very high. In summary, capacitors love high frequencies. To understand the relationship between current and frequency, consider the two halves of an AC cycle. On the first half, current is flowing towards the plate of the capacitor and the bulb is lit. On the second half, electrons are going to be flowing in the opposite direction. The electrons move back and forth around the circuit, passing through the lamp and charging the capacitor one way and then the other. Remember, the electrons do not pass through the capacitor. The higher the frequency, the less time there is for a charge to build up on the plates of the capacitor and oppose further charges, because it's the charges built up on the plates which oppose the flow of further electrons going towards the plate. So if I don't have that many electrons, that many charges on the plate, I'm going to have a small amount of oppositions to further charge. A small opposition means a small impedance and a larger current. So more charge is transferred in 1 second and the current is larger. Example 1. Circuit shows an AC supply of voltage, 6 volt RMS, a lamp and a capacitor. What happens to the brightness of the lamp when the frequency of the supply is increased? Well, if the frequency is increased, that means the impedance of the capacitance is going to decrease, and therefore the current increases and the lamp glows more brightly. Part B, what happens to the brightness of the lamp if the AC supply is replaced by a 6 volt DC supply? Well, a DC supply means that we've only got one direction of the flow of current. So the capacitor is not going to continually charge and discharge. 6 volts DC is equivalent to 6 volts RMS, and so the initial brightness of the lamp is going to be the same, but the lamp will quickly dim and then go out. Example 2. A resistor and capacitor are connected in series with an AC supply of voltage Vs as shown below. The voltage across the capacitance, Vc, is produced across the capacitor. The frequency of the supply can be changed. When the frequency of the supply is 100 Hz, the ratio of the voltage across the capacitor to the voltage across the supply is equal to 0.5. The frequency of the supply voltage Vs is now increased to 1000 Hz, but it has a constant amplitude, remember. Explain whether the ratio of voltage across the capacitor and voltage across the supply will increase, decrease, or stay the same. Well, if the frequency increases, the impedance of the capacitor decreases. The impedance of the capacitor, remember, is the opposition to the current. So we can almost think of it as like the resistance of the capacitor. And we know if the resistance of an element decreases, then the potential across it is going to decrease it as well. So voltage is proportional to the impedance, so the voltage across the capacitor decreases, which means the voltage across the resistor increases. Therefore, the ratio between VC and VR is also going to decrease as the supply voltage is constant. Example 3. In the circuit shown below, the output voltage of the signal generator is kept constant. We have a potential divider on the left-hand side and another potential divider, but this time with a resistor and a capacitor on the right-hand side. Explain what effect, if any, there will be on the size of the voltages V1 and V2 when the frequency of the signal generator is decreased. Well, if F is decreased, the impedance of the capacitor is going to increase, but the impedance of R1 and R2 and R3 are all constant. That means the effective resistance of the capacitor here is going to increase. So there's going to be a greater amount of potential across it. V1 is constant. And since V is directly proportional to the impedance, VC also increases. And so V of R2 decreases. V2 will also decrease.